it should be 9 and 10, right? Just one. 10 there, I hope.
Yeah.
Oh, it is.
Why do you skip the rest of chapter 9?
Because, I think I told you,
Yeah, you could.
because it's one of those concepts in chemistry that's extremely difficult, and I can spend a week and a half trying to teach it to you, and then you not understand it, and then lose a week and a half at the end of the year that I could have taught you something that you will understand.
It's gonna be like a response test in those 10 different chapters.
All right. So really what chapter 9 is about is kind of we talked about the valence bond theory and the VSEPR theory. Well, there's actually a theory that's better than that, but way more complicated than that. So that's essentially what this chapter is over. And it deals with hybrid orbitals, which I will introduce at least what hybridization is and how hybrid orbitals are formed, but we're not going to talk about bonding orbitals and anti-bonding orbitals and how you get magnetism out of bonding and anti-bonding orbitals and all that fun stuff. Okay, so in chapter 8 we really spent a bunch of time talking about Lewis structures and predicting molecular geometry through the VSEPR model, right? R type, R square pan, something. I don't know.
Still, no, wait, our square
Still
square
tight,
pants,
but
still tight, but still too loose.
Tight,
Yeah.
probably one of our better acronyms.
Yeah,
Okay.
so much.
So, this beginning chapter, we're going to discuss how the orbitals act when they bond, and that's going to be formed due to hybridization, or hybrid orbitals are going to form. So here's what hybridization is. It's the mixing of native orbitals. What do you think they mean when they say native orbitals? Yeah, the original orbitals that they had, right, as P, D, and F, right? So it's the mixing of native orbitals of a given atom to form special atomic orbitals for bonding, aka taking the original orbitals and forming hybrid orbitals that they would use to bond. Does that make sense? Let me show you. Let's just talk about the CH4. Now, I don't know how much room I've given you and whatnot, so that does say describe the bonding of ammonium. I didn't give you a whole bunch of room to show this. Maybe you can put it in the top right corner. Okay. So we're going to examine CH4. Okay, we know that your central atom, we're going to do the Lewis structure. Like this. If I were to do the orbital notation of that carbon, I'm just going to do its valence electron as orbital notation. Does that make sense? So I'm not going to worry about the 1s. I'm just going to do the 2s and the 2p of carbon. It would look like that, correct? If I do the orbital notation, that's what the... Just because it's not going to be involved in bonding. It's just the valence electron. Did you get hit in the eye?
Apparently that girl's going to Illinois State.
She had like 40 points. She had like all the points.
Who?
They had like a D1 player that they played.
Really?
She
Is it
was
real
like
good?
6 foot.
Like 6'2".
Should wake up.
Yeah.
Cool. My life of a rector. Alright. Anyway, so the reason why, again, I'm only showing the second energy level here is because this is your valence orbitals here, your valence electrons. Okay, and if we were to start doing the Lewis structure, we would see this. That suggests that there are 4 unbonded or unpaired electrons, right? This is only a pair, that there are 2 unpaired electrons. Do you see a problem here? Okay? So they had to come up with a new, essentially a new theory to explain how something that only has 2 unpaired electrons can form 4 bonding sites. Okay? And so what they came up with is this process of hybridization. There's also another thing that they had to somehow fix, and it was that the s orbitals and the p orbitals don't have the same energies, correct? Which one's higher energy? The p, right? Okay? And assuming we took out the impact that the molecular environment has on the bonds, all of these bonds would be the same energy. But if you had like a p orbital overlapping with the 1s of H and a s orbital overlapping with the 1s of H, you would expect 2 different bond energies, right? 2 different bond lengths, if that were the case. Okay? So what they did is they said, we are going to form hybrid orbitals. So this is what the energy will look like. Say that's the 2s, a little higher energy is your 2p, and it forms hybrid orbitals. Okay? It actually forms 4 hybrid orbitals of the same energy, and these hybrid orbitals are called sp3. Any idea why it's called sp3 hybrid orbitals? Yeah, because we are hybridizing 1s orbital and 3p orbitals. Right? There are 3 orbitals and 1s orbital for a total of 4 orbitals, right? Coming from an s and p. Okay, so essentially what they say is they take the electron, 1 electron from the 2s, form these new hybrid orbitals so that it actually looks like this, where you have 4 unpaired electrons and allows for 4 bonding sites to appear.
The last 2, the 2 outer.
You're going to do your valence electrons is what you're going to hybridize. Yep. I'm not 100% sure what those core electron orbitals are going to do. I would assume they remain the same, but I don't know that I've ever been taught what happens with those, and I don't think it really is that important. Okay, so what do you have? We'll get to this at the end, but
So how does that relate to the exceptions in the transition elements?
okay. So, whenever a set of equivalent tetrahedral orbitals is required by an atom, this model assumes that the atom adopts a set of sp3 orbitals, or the atom becomes sp3 hybridized. What that simply means is any tetrahedral shape is going to form sp3 hybrid orbitals. And I think at the end of this note packet, you will have a table that summarizes this. So any 4,4, 4,3, 4,2, or 4,1 are going to be sp3 hybrid orbitals. Anything that has 4 regions of electron concentration is going to form this type of hybridization. Does that make sense? We're going to talk about what happens with 3 regions, what happens with 2 regions, what happens with 5 regions, and what happens with 6 regions. Okay, those are going to be a little bit different. Okay? And this is something you're going to need to know well enough to be able to do an essay question on. Just giving you a heads up. Okay, now let's look at ammonia. What's ammonia? Okay, that's ammonia, Maya. You're close though. Yeah. Okay, so let's first remember what the shape would be going back before Thanksgiving. What shape would that be? Yep. And pyramidal is a tetrahedral shape. Why do I say that? It has 4 regions. Okay, so it says describe the bonding. So we're going to have to describe how these orbitals are going to overlap. So here's how I would do it. I would say, if I were to do this on an essay question, I would say 3 bonds form. You might want to write this down. Okay? When 3 sp3, why is it sp3? Four regions. Okay? Now only 3 of the sp3 orbitals are going to be bonded. Now I'll explain that in a second. Okay, so 3 sp3. So nitrogen is sp3 hybridized. One of them is going to contain a lone pair. The other is going to overlap with the hydrogen here. One's going to overlap with the hydrogen here. One's going to overlap with the hydrogen here for 4 of them. Does that make sense? Okay, well, what is the sp3 orbital going to overlap with of the H? What orbital is the H going to have? Just the 1s. Ouch. And I could maybe say nitrogen, 3 bonds of nitrogen form, or I probably should have put something in there that the sp3 orbitals were nitrogen's orbitals, but you can kind of make that assumption if you state that the 1s is hydrogen, the other one has to be the nitrogen. Does that make sense? Okay? Then I got to somehow explain where that last sp3 hybrid orbital and what it's doing. What is that last sp3 hybrid orbital doing?
It's a lone pair.
Yeah, it's going to contain a lone pair. Hybrid. Now this is one of the easier ones. It's going to be a little bit harder. Okay? The thing that you got to know is anytime you got 4 regions, you're going to have sp3 hybrid orbitals that are formed. That means all of the s and all 3 of the p's are going to form hybrid orbitals. Not in every case will they all form hybrid orbitals, and we'll talk about that as we progress here. Questions so far? Overly difficult? We're going to get into the book and we'll look at some of these orbitals, what they look like, and so forth. All right. Some of this should be a little bit of review from last year, or for some of you 2 years ago. I don't know if you guys remember sigma and pi bonds at all.
Yeah, I do.
Okay? So sigma bonds are really a type of covalent bond where orbitals overlap, and we talked about how they overlap end to end, but we're not going to worry about that. But where they overlap is important. On a center line running between the 2 nuclei of the atom. Do you remember what we called that line last year? Anybody remember that?
Axis.
Bond axis, yes. Okay? Then we talked about pi bond is going to be not on the bond axis. We would say above and below the bond axis when p orbitals overlap side to side. And I'll show you this when we get into looking at a few of these models here in the book. Actually, you can flip right now to 406, and you can see what that NH4 molecule would look like. Since we just got done doing that NH4. Do you see the green orbitals are representing the sp3 hybrid orbitals? Those are different looking than an S and a P would. Everybody see that? Everyone except Emily who hasn't turned there?
Page 406.
406. The top one is your carbon, but I'm just talking about the bottom one is your nitrogen, your ammonium. Okay? Now, if you can remember, sigma bond was stronger than a pi bond. Does anybody remember why a sigma bond would be stronger than a pi bond? Less energy. Well, that's
Well,
true.
it's only in that order,
That's also true. Think about where a sigma
Oh,
bond
it's
happens.
it's two regions, or whatever it is, it's head to head, it's not just grazing each other there
Well, that's also true, but where is it occurring?
on the bond axis.
On the bond axis. Okay, so your overlapping orbitals are happening right in between the two nuclei.
Yeah.
So it's going to be a lot stronger, held a lot tighter, less energy, okay? And a pi bond happens when you've already had a sigma bond, and it does not happen on the bond axis. Okay, so if you remember, a double bond is always going to consist, the first bond of a double bond is going to be a sigma, and the second one's going to be a pi bond, and we'll talk about how that works in a sec. A triple bond is going to have one on the bond axis and two, a knot on the bond axis. And again, we'll talk about that as we progress here. I don't want to do N2 yet. Do you have space at all for C2H4? You don't, do you? Okay, well maybe you split that example section into two examples. I want to show you what this guy's going to do here. Where's my nice marker here? I'm going to show you what this guy's going to do. C2H4. First of all, this is what it would look like from a Lewis structure standpoint. All right, how many regions does this have? Talking about the carbon central atoms. Carbon central atom.
Oh,
3. Okay? So these would be the unhybrid orbitals, or their native ones. The P would have more energy than the S, correct? Okay, well there's only 3 regions here. So what ends up happening is only 3 hybrid orbitals need to form. And here's what this looks like. You form sp2, and there's one p orbital that is left unhybridized. And I'll explain where this p orbital comes into play. Okay? Turn your books to 408. This is a little bit trickier. We have to spend a little time focusing on this. At the top here, this is your orbital, your orbital example of what this is going to look like. Okay. Your blue guys are going to represent what? Your hydrogen. That's the 1s orbital. Okay. So what's going to happen here is the 1s will overlap with what from the carbon? What's the orbital going to? The carbon orbital is going to be? What hybridization is it? sp2. So 1s overlaps with sp2. sp2 with 1s. sp2 with 1s. Okay, so far I've accounted for 2 of the 3 sp2 hybrid orbitals. Why do I say 2 of the 3? Why isn't there 4? Why isn't there 4 sp2 hybrid orbitals? Yeah, because 1 was left unhybridized, right? 1 stayed in its original p orbital state. And I'm going to show you why that is. Okay? Now here, the first bond of the double bond is an sp2 of 1 carbon overlapping with an sp2 of another carbon on the bond axis. So if you look at your picture here, that is represented by the two green orbitals overlapping. Does everybody see it in your picture, the top? Okay, do you see the three sp2? One of them is overlapping with hydrogen, second one overlapping with hydrogen, and then there's one carbon-carbon overlapping of sp2. Everyone see it? Okay? If you remember, a double bond happens when you have a second bond or a pi bond overlapping sides of p orbitals. So if you look to the picture on the right, everybody see the picture on the right? You've got the yellow p orbitals. You see them? Everybody following?
Yeah.
Okay? When you squish those guys closer, do you see how those p orbitals would overlap above and below the bond axis?
Yeah.
Everybody? I need a yeah from everybody.
Yeah.
So what ends up happening is this second bond, the second bond of the double bond is when the unhybridized p orbitals of each overlap above and below the bond axis. So if I were to answer this question on a short answer or a essay question, this is how I would probably state it. I would say carbon is sp2 hybridized with one unhybrid p orbital remaining. Okay? Then I would say an sp2 of carbon will overlap with the 1s of hydrogen for all four of them. Okay? Then I would say that the sp2, the remaining sp2 orbitals of the carbon, is going to form the sigma, or the first bond of the double bond. Does that make sense? And the second bond of the double bond occurs above and below the bond axis when the unhybridized p orbitals overlap. Following? Questions? Okay. What happens when we insert a triple bond?
Can you show us how we would draw the arrows for to your right?
Here?
Yeah.
It's going to be. Oops. What were we doing? Carbon?
Oh, it wouldn't change.
Yeah, you still need those four bonding regions.
Yeah, yeah.
Okay, let's do. Can I erase this now?
Yeah, yeah, yeah. Thank you.
Oh, too nice. Same situation here. From an energy standpoint, we still have 2p is higher energy than 2s. Now this is nitrogen, so it's going to look a little different. Nitrogen has one more. Okay? In this situation, if I were to draw the Lewis structure here, this is what it would look like. Okay? How many regions are there?
Two.
There are two. When you have two regions, you're only going to form two hybrid orbitals. And those are going to be sp hybrid orbitals, and you will have 2p orbitals unhybridized. Now what do you think those 2p orbitals are going to be used for? What was the p orbital used for in the previous example? The second bond of the double bond, or forming the pi bond, right? Now that we've got a triple bond, we need two p orbitals to form the two pi bonds that make the triple bond. Does that make sense? We'll go through this here. Okay? So, we have sp. What is going to be, where are the sp orbitals going to be in this situation? Both these are sp hybridized with two unhybrid p orbitals. Where are the sps going to be? The what? Just going over our heads a little bit.
Like one of the bonds,
Yeah, but which one?
the bottom one.
It's going to be the first. So we know this bond, the first bond of the triple bond, the one that happens on the bond axis, the sigma bond, is going to be sp overlapping with sp. So I've used one of the two sp orbitals of my nitrogen. What is going to be, where is the second sp orbital going to be? Is it going to be the second bond, the third bond, the lone pair? What's it going to be?
It's not gonna be the, other bond.
It's not going to be our bonds. What does it have to
So
be?
it's the one of the pairs, you pick a lone pair, or they both are.
Well, they both need two SPs. So there's this nitrogen's two, and there's this nitrogen's two.
Oh,
Does that make sense? And then these two pi bonds, so I can maybe say this is a sigma bond. And these two pi bonds are p orbitals overlapping above and below bond axis. So how would I describe this on an essay question? I would say sigma bonds form when one sp orbital overlaps with another sp orbital from the nitrogens. And then I'd probably say something like each nitrogen uses its last sp orbital to hold the lone pair. I'd say something like the second and third bonds, which would be your pi bonds, right? Correct? So the second and third bonds of your triple bond form when unhybridized p orbitals overlap. Handwriting's kind of sloppy. If you look, I think on .410, it gives you
So where's the bond axis?
So when we actually show the triple bond here, it appears that they're all on the bond axis, but in reality, the single bonds is right on the bond axis, and the double bond is above and below, like on the X, or on the Y, and then on the Z. It's kind of hard to show that in 3 dimensions. So, like if you, so let me see if I can find it. Yeah, it's actually 411 is your nitrogen here. So if you look at 411, the teal color, I don't know if that's what you call that, the teal color represents your sp. You notice how nitrogen only has 2 sp orbitals. Everybody see it? Okay? The outside sp orbitals are containing the what? Lone pairs. Do you see the sp that's right in between the nitrogens? Okay, that's the sp that's on the bond axis. Does that make sense? If you were to squish that or compress it, and the reason why they show it apart is so it would be very difficult to see everything if you compress it all. Does that make sense? Do you see how those p orbitals, if you got them close enough to each other, that they would overlap above and below the bond axis in a 3-dimensional pattern? That's what that pi bonds are going to look like. Okay? Questions? It's a lot.
So a double bond will always have one, like one repeat, and then triple will always have two.
So if you're going to form a double bond, you're going to have, you're probably sp2 hybridized. You could be, okay, I shouldn't always say that. So like something like this. Okay, this forms 2 double bonds. So this has 2 regions, that's going to be sp. And the double bond here is going to be one of carbon's p's and a second carbon's p. So in that case, you can't assume that just because it has double bonds that it's always going to be sp2. Because if it has 2 double bonds, it would have to be sp. Does that make sense? So what you would have, your three orbitals are going to be 2 sp and 2 unhybridized p's. Oxygen is going to be 1, 2, 3. So what would oxygen's hybridization be? Yeah. It's really as simple as knowing how many regions it has. If it's 3 regions, what's its hybridization? sp2. So that's an sp2. That's an sp2. And the first is an sp2 overlapping with an sp. Everybody see it? Okay? And then a p overlaps with a p to form the pi. It's a lot, I know. And do you see why I'm not going further on with this stuff? So then this becomes, this is sp overlapping with sp2. Those are sp2s. That's sp2. So do you see how you have 3 sp2s on the oxygens because it has 3 regions? Carbon has 2 regions, so there's only 2 sps. An sp here and an sp there. Well, if you have 2 sps, that means there are 2 unhybridized p's, correct? Well, carbon has one of its unhybridized p here, and the other is here. This comes from oxygen, and the other p comes from oxygen because it only has one unhybridized. Yes?
So the nitrogen one, there's 2 sps for each nitrogen because there's 2 regions for each. Is that how it works?
It's always based on regions.
Okay.
Yep.
Okay.
Okay, so if you flip the page, you should see something like this, correct?
Yeah.
You're going to have to get familiar with this. We've talked about most of these. We talked about 2 regions is going to be sp hybridized. What is going to happen? What's going to be left unhybridized? How many of them? There's 3 total p's, right? If you only hybridize 1 p, you have to have 2 unhybridized. How about this one? There's only going to be 1 unhybridized. How about here? None. There's no, all of them got hybridized. This is where it gets a little goofy. So something like this, right? Do you remember doing a Lewis structure that looked like this? How could something with 2 bonding sites form 6 bonds? So what would happen here? I know this is going to be a little bit above probably where you're ready for, but I probably should do 3 because it's not going to happen in the second energy level. So it looks like this. Okay, so that's 6 electrons, 6 valence electrons. Everybody see it? That's what it looked like. Well, this one and this one will be promoted to the d orbitals. And you're going to form 6 sp, nope, sorry. 6 d2 sp3. So 1, 2, 3, 4, 5, 6. That makes sense? Not much. It's a lot, I know. It would do you some good to read. I don't want to read though.
You can just make me crazier more.